In this video we introduce HI-SLAM2, a monocular SLAM system designed to achieve both high-fidelity rendering and accurate scene geometry. Our system takes a monocular RGB stream as input and constructs on the fly a dense 3D map represented by Gaussian splats. Monocular geometric priors are extracted online, and the scales of depth priors are aligned to improve depth estimation. Dense Visual SLAM module estimates camera poses and builds a semi-dense proxy depth map. These components are fused to build a 3D Gaussian representation that encodes both geometry and appearance, enabling photorealistic rendering and accurate mapping. In many SLAM methods, there is often a trade-off between rendering quality and geometric accuracy. However, both are essential. Geometric accuracy refers to capturing the true shape and structure of a scene, which is critical for tasks such as robotics, navigation, and 3D reconstruction. Rendering quality, on the other hand, focuses on visual realism, which plays a key role in applications like augmented and virtual reality. To bridge the gap, let's look at the landscape of existing approaches. Dense Visual SLAM focuses on geometry and achieves real-time tracking and mapping. However, it struggles with rendering quality and suffers from high-depth outlier rates. Radiance-based SLAM excels in visual quality using radiance field representations, but often lacks accurate geometric maps, required depth camera, and lacks loop closure. Monocular reconstruction methods combines rendering and geometry using monocular priors but is offline and computationally heavy, unsuitable for real-time SLAM. None of these approaches fully satisfies the demands of real-time operation, geometric accuracy, visual realism. Here is the pipeline of our method, which consists of 4 main modules operating concurrently. Online tracking estimates camera poses and selects keyframes. It performs local bundle adjustment and incorporates monocular geometric priors through a joint depth scale adjustment step to resolve scale inconsistencies present in the depth prior. The estimate states are synchronized efficiently through a shared keyframe buffer. Online loop closing detects when the camera revisits a previously seen area and applies Sim3 pose graph bundle adjustment. This corrects both pose and scale drift on the fly and feeds the updated poses back to the system. The mapping module continuously updates the 3D Gaussian map. As new keyframes are added, or when global updates by loop closure, the system optimizes the Gaussian splats to align with both the observed images and the geometric priors. Final refinement is an offline step that further improves overall accuracy. It performs global bundle adjustment and jointly refines camera poses and the Gaussian map using all collected keyframes, producing the most precise reconstruction. Now let's look at the results of HI-SLAM2, starting with the synthetic replica dataset, which provides photorealistic indoor scenes. We show side-by-side comparisons with prior methods. Our method delivers both more accurate geometry and more realistic appearance than our baseline, HI-SLAM1. Fine details such as wall textures and furniture are well preserved, and the underlying geometry is more precise. Objects are correctly shaped. Compared to Glory SLAM, which offers comparable rendering quality, our method achieves noticeably better geometric accuracy. This improvement is made possible by our integration of monocular geometric priors and dense visual SLAM optimization, allowing us to capture both appearance and structure more faithfully. Scanet presents real-world indoor scenes with challenges such as motion blur, varying lighting, and sensor noise. Despite these, our method remains robust and reliable. Compared to Splat SLAM, our reconstructed mesh is significantly more geometrically accurate, preserving fine structures such as thin chair legs, while also maintaining smooth surfaces in background regions like white walls and floors. We further validate our method on outdoor driving scenarios, where the rendered images from our method capture significantly more detail such as road markings and lamp poles, compared to baseline methods such as MonoGS and OpenGS SLAM. ETH 3D SLAM benchmark includes challenges such as rapid motion and varying lighting conditions. In the example sequence, Droid SLAM suffers from both pose and scale drift, resulting in a big absolute trajectory error. Mast 3R SLAM achieves accurate pose tracking but produces inconsistent scene geometry. In contrast, our method achieves the highest accuracy. Leveraging geometric prior helps stabilize motion estimation during fast movements, and the immediate loop closing quickly corrects accumulated drift. We evaluate our system on our own robot through a field test conducted in a large factory hall of approximately 2,000 square meters. The robot is equipped with a stereo camera, however only the left camera input is used for our monocular pipeline. As shown, the black triangles indicate keyframes along the robot's trajectory, while novel views are rendered by virtually roaming through the environment. Notably, our system retains high fidelity even at novel viewpoints far from the training keyframes, with hardly any floaters observed thanks to the accurately modeled underlying geometry. As an extension, we integrate semantic understanding into our framework by assigning semantic colors to each Gaussian. After reconstructing the scene, we can further apply a spatial language model, such as spatial LM, to reason about the environment. This demonstrates the potential of using rich geometric maps as a foundation for intelligent spatial understanding. Thank you for watching. Please visit our project page to explore the open-sourced code, paper, and additional demos.